Hi everyone, welcome back to the channel. Today's video dives into one of the strangest chapters in Earth's history, the winter that may have wrapped our planet in ice from pole to pole. If you enjoy this kind of slow science-based storytelling, please remember to like the video, subscribe and share it with someone who loves cosmic and Earth mysteries. Thank you so much for spending your time here, it really helps this channel grow. And I am curious, what time of day are you listening to this and where in the world are you watching from? Let me know in the comments. Light from a small grease lamp wavers against a pale stone wall and reveals an animal that no longer walks the valleys above. A dark line curves into the shape of a horn, or perhaps a tusk, and behind it great antlers spread outward until they almost touch the uneven ceiling. As the light moves, the cave seems to fill with motion. Horses stretch into a gallop. Heavy-bodied bison lower their heads. Long vanished aurochs and giant deer appear in overlapping layers painted and engraved by hands that return to the same surfaces generation after generation. This cave in what is now southwestern France, known today as Lascaux, is not a shelter for living herds but an archive of an Ice Age landscape and of the people who endure it. Outside, cold wind sweeps across a treeless plain. The ground is hard with permafrost for most of the year, and in winter the air is filled with fine dust driven off distant ice sheets by persistent gusts. Bands of hunter-gatherers move along the edge of this frozen world, wrapped in the furs of the same animals they follow. They pass reindeer, woolly rhinoceroses and mammoth that scrape through snow to reach buried grasses. To them the cave is a rare refuge, a quieter pocket in a harsh environment, where the sounds of the wind fade and time seems to slow. Modern methods of dating charcoal and mineral deposits suggest that many of the paintings at Lascaux are created around 17,000 years ago, during the later part of the last Great Ice Age. At that time, much of the northern half of the planet lies under enormous ice sheets. These continental slabs rise taller than any human-built structure and flow slowly outward from centers near the poles. Average global temperatures are several degrees colder than they are today, and in regions closer to the ice margins the air is not only cold but dry with little snowfall to renew the surface. Sea level stands around 125 meters lower than at present, because so much water is locked up as ice on land. The coastline of every continent is shifted, exposing broad shelves where waves now roll. In Europe and North America, ice extends far south of its current limits, and the habitable zone for the people of Lascaux is squeezed into a belt of steppe and tundra between the ice sheets and the warmer south. Here a mosaic of grassland and scattered shrubs supports great herds, and with them the humans whose survival depends on those migrations. The images on the walls show this world in stark and careful detail. The artists give their animals powerful shoulders and alert eyes. They understand how a bison's fur hangs, how a horse's mane lifts in the wind, how a mammoth's trunk curls as it walks. Among the familiar forms appear creatures that have no living counterparts in these valleys, such as the giant deer with its enormous antlers and the cave lion that stalks the edges of the herds. Their presence tells of a time when climates and ecosystems differ sharply from those of modern France. To a contemporary visitor, the paintings are a glimpse into a colder Europe, but to the people who make them, they are part of daily experience as ordinary as the changing light on snow and ice. Still, the very act of painting in these deep chambers suggests reflection. Far from the rush of the hunt and the risk of exposure, the cave allows space for memory. Scenes of pursuit, injury, and perhaps ritual are layered into compositions whose exact meanings are lost, but whose context can be reconstructed from the geological and climatic record. Scientists now refer to the peak of this last ice age as the last glacial maximum, a period centered around 26,500 years ago, when ice sheets reached their greatest extent in the current cycle. Sediment cores from the ocean floor, bubbles of ancient air trapped in polar ice, and patterns of fossil pollen all indicate colder conditions, widespread aridity, and powerful winds that carry fine dust across continents. Yet for all its severity, this age is not a complete planetary freeze. Tropical forests persist near the equator. Temperate regions in parts of Africa, Asia, and the Americas remain free of ice even if they are cooler and drier than today. The human population retracts into scattered refuges, but it does not vanish. Plants continue to grow where conditions allow. Oceans remain open, circulating heat and nutrients around the globe. There are hard limits, but also pockets of relative stability. The people of Lascaux live close to one such boundary on the dividing line between the livable and the lethal, and their paintings mark that tension on stone. This contrast becomes important when researchers look away from the late Ice Age and back into much deeper time. If a climate as fierce as the last glacial maximum still leaves room for unfrozen seas and green valleys, could there have been earlier times when the cold goes further, when ice reaches not only into mid-latitudes but all the way to the equator? Some of the same methods that reveal the age and environment of the Lascaux paintings can be extended into rocks that formed hundreds of millions of years before any human walked the earth. Layers of sediment with certain grain sizes scattered larger stones embedded in finer mud, and polished, scratched bedrock surfaces all tell of glaciers that once ground over them. At first, such deposits seem to confirm a simple picture, in which ice appears mainly near the poles and in high mountains as it does in the present and in the time of Lascaux. However, as more sites are studied, a new and more troubling pattern starts to emerge. Some of these glacial signature appear in rocks that, when their original position on the globe is reconstructed, seem to have formed near ancient tropical seas. The cave on a cold evening in the late Ice Age thus stands at the threshold of another story. Its walls preserve the memory of a regional winter that lasts for thousands of years, a winter that is harsh but survivable. The science that deciphers that memory points further back to intervals in Earth's history, when cold may have gone far beyond anything the Lascaux hunters could imagine. In those much older ages there might have been no temperate refuge a short journey south, and no ice-free oceans for winds to cross. The paintings of mammoths under a low ceiling of rock therefore serve as an entry point linking the human story of endurance at the edge of an ice sheet to the planetary story of ice that may once have wrapped the globe itself. Snow blows across the Antarctic plateau in long pale sheets as an expedition party moves steadily inland from the coast. The year is early in the 20th century, and wooden huts, canvas tents and sledges hauled by dogs mark one of the first systematic attempts to survey this part of the southern continent. Among the group is a young geologist from Australia, Douglas Mawson. He measures, observes and records almost everything he encounters. The men travel over featureless white ground where distance is hard to judge, and the horizon is a faint blur between snow and sky. The temperature remains far below the freezing point of seawater, and the wind drives ice crystals into exposed skin. Mawson and his companions move in teams tied to sledges that carry food, fuel instruments and canvas. To them, ice is not an abstract climatic concept, but a medium they live on, sleep on, and try to understand with every step. Their journey becomes a severe test of endurance. When one sledge breaks through a hidden crevasse and vanishes with a man-dog's and a large part of their supplies, the expedition changes character. It is no longer a survey with generous margins, but a calculated retreat based on dwindling food and the constant risk of further accidents. The remaining dogs are gradually slaughtered and eaten. Fat and muscle that once pulled the sledges now fuel the humans who still drag them. Illness follows, and one of Mawson's two remaining companions dies after days of confusion and convulsions, later linked to chronic poisoning from dog liver rich in vitamin A. Mawson continues alone across the ice. The surface seems unchanging from day to day, yet he knows that he covers real distance measured carefully on the map. The hut at the coast with its radio and stores becomes an abstract point he aims for while negotiating cracks, drifts and pressure ridges. When he finally returns thin and physically damaged, he finds that the ship assigned to take the party home has already departed. Bad luck in timing adds another forced winter to his stay in Antarctica. During the long darkness, he orders sorts and interprets the scientific results of the expedition. Samples of rock and ice cores, measurements of temperature and wind, and observations of wildlife fill his notes. His survival story captures public attention when he eventually returns to Australia. But for him, the most lasting part of the experience is the geological insight it offers. He has walked on modern ice, measured the conditions under which it accumulates and flows, and seen how glaciers carve and deposit. These memories follow him back to his main academic work. In Adelaide, as a professor of geology, Mawson begins to examine rocks from ancient parts of the Australian continent that show signs of past glaciation. Across thousands of kilometres of terrain from South Australia into what is now the Northern Territory, he and other researchers document thick successions of poorly sorted sedimentary rocks. They consist of mixtures of boulders, pebbles, sand and mud that appear to have been dropped and smeared rather than sorted by flowing water. In places, large clasts sit in a finer matrix, and scratched, polished surfaces on underlying rocks align with the direction of ancient ice movement. These are classic indicators of glacial till material left behind by glaciers that once moved over the landscape and melted. The age of these rocks is striking. They are not associated with the recent ice ages of the Pleistocene, but with a much older interval in Earth's history, the Neoproterozoic era, more than 500 million years before the first animals with hard skeletons appear in the fossil record. At the time Mawson studies them, the idea of continents shifting their positions over geological time is not yet widely accepted. Without an established framework of plate tectonics, it is natural for him to picture Australia more or less where it is now, under a mostly warm to temperate sky. In that case, the presence of repeated widespread glacial deposits on a continent that presently includes some of the driest land on Earth demands an explanation. How could thick ice once cover ground that now lies under deserts and open woodland at relatively low to mid-latitudes? Drawing on his personal experience with modern ice sheets in Antarctica, Mawson suggests that these ancient Australian deposits might be part of something even larger. Perhaps he reasons they are evidence of a time when ice extended far beyond polar regions, engulfing much of the planet. In modern language, he's imagining a kind of global or near-global glaciation. His proposal is cautious yet bold. It grows from physical evidence and rocks combined with simple geographic assumptions. Later developments in geology alter the interpretation of his Australian data. As the theory of plate tectonics gained support in the mid-20th century, geologists learned to reconstruct the past positions of continents by reading magnetic signals preserved in iron-bearing minerals, and by matching ancient mountain belts and sedimentary sequences across now-distant landmasses. When these new tools are applied to the Neoproterozoic glacial deposits of Australia, they indicate that parts of the continent once lay closer to the poles than they do today. In that configuration, the presence of ice becomes less surprising, and there is no need to invoke a planet-wide freeze to explain a single region. Mawson's original global hypothesis seems to be weakened. His glacial rocks mark intense local or regional cold during a time when Australia sits nearer a pole rather than a universal deep freeze. Yet his idea does not disappear. Instead, it shifts focus. The combination of ancient tillites in Australia, similar deposits on other continents, and new reconstructions of continental positions does not close the case against extreme glaciation. It opens a new one centered on an anomaly that cannot easily be explained away. As more data accumulate from different parts of the world, some glacial indicators appear in rocks that, according to paleomagnetic measurements, formed at low latitudes near the equator. If those measurements are correct, then ice did not merely follow continents into high latitudes. It occupied zones that usually host tropical oceans and rainforests. the question that Mawson raises in general terms remains in a new form. How far can ice spread on a planet like Earth, and under what conditions? The long sensory memory of his Antarctic march becomes one element in a much wider investigation. What he feels in his face and hands as wind slices across the Antarctic plateau is an immediate intense cold. What the rocks he studies later record is a cold extended across millions of years, thick enough to leave stacked layers of sediment hundreds of meters deep. Between these two scales lies deep time, and it is in this interval that the possibility of a snow-covered Earth begins to take shape. Mawson's experience links the modern, relatively modest ice age that humans inhabit with a far older series of events. His interpretation of Australian rocks is corrected in detail but influential in spirit. It encourages geologists to think of climate as a system capable of more extreme states than those directly observed. It invites later researchers to treat every scattered patch of ancient glacial sediment not as an isolated curiosity, but as a potential piece of a coherent pattern. In this way, an expedition that begins as a national effort to explore and map a remote part of Antarctica becomes one of the early human steps toward recognizing that Earth's past climate may have included intervals when cold pushes the entire system almost to its limits. In many mountain valleys today, the signs of recent glaciers are obvious. Bare rock near the head of a valley is smoothed and shaped into gentle curves. The lower slopes are strewn with loose stones and boulders dropped when ice retreats. Lakes fill over deepened hollows, and ridges of unsorted debris mark the places where the ice front once pauses. Geologists learn to read these features on modern landscapes before turning to older rocks that preserve similar traces. With that training, they begin to recognize ancient glacial deposits from times long before any human is alive to witness them. Pieces of the story appear first on different continents. In North America, Europe, Africa, Asia, and Australia field teams describe rock formations that share the same basic structure. At their base lies a scoured surface, a bed of older rock, polished smooth, and often incised with long, almost parallel scratches known as striations. Above that rests a mixture of fragments of many sizes from fine clay to large rounded or angular blocks, all packed together without the normal sorting that river currents or waves would produce. In many places, this glacial till is hardened into rock and is called a tillite. It sometimes contains isolated larger stones in a finer background, as if boulders have been carried in from elsewhere and dropped into soft mud. Higher in the sequence, there may be layers of more ordered sediment, perhaps deposited by meltwater streams or in lakes that form at the edges of retreating ice. Taken together, these elements describe the presence of glaciers that grind across bedrock drag and drop cargo, and then melt away. When these deposits are found on continents that today lie in temperate or polar zones, they seem to fit comfortably into the idea that Earth passes through many cold episodes. However, the geological record reveals not just one ice age, but several spread over billions of years. Some are local, confined to particular mountain belts, others are more extensive. The Neoproterozoic period between about 800 and 600 million years ago attracts attention because it appears to host repeated and unusually widespread glacial layers. In South Australia, Canada, Namibia, China, Siberia, and elsewhere, rocks of roughly similar age show the hallmarks of glacial influence. This is already remarkable, but the true puzzle emerges when scientists consider where on the ancient globe these rocks form. Earth's magnetic field offers a way to estimate the latitude at which a rock is created. When lava cools or sediment settles, tiny grains of iron, rich minerals inside, can align with the magnetic field of the time, just as compass needles do now. Once locked in place, these mineral grains store information about the direction and strength of that ancient field. Many millions of years later, geophysicists can measure their orientation in the laboratory and compare it with models of how a magnetic dipole field behaves around a rotating planet. This comparison allows an estimate of the original distance from the magnetic equator at which the rock formed. The method is known as paleomagnetism. It does not usually give precise longitude, but it yields useful constraints on latitude. When paleomagnetic measurements are made on the Neoproterozoic glacial rocks, a pattern begins to emerge that does not match expectations. Several of the best studied tillites and associated sediments appear to have formed at low to moderate latitudes in zones that would today correspond to the tropics or subtropics. In other words, evidence for ice lies not only in rocks that once rested under polar skies, but also in rocks that were laid down near the ancient equator. One example comes from the Norwegian archipelago of Svalbard and parts of Greenland where late Neoproterozoic sedimentary sequences contain clear glacial indicators. Paleomagnetic data suggest that at the time of their formation, these regions sit close to the equator rather than near the poles. Similar data from Namibia, where spectacular cliffs reveal thick glacial deposits overlain abruptly by carbonate rocks, point toward low latitudes as well. If the measurements are correct, then ice once existed within a belt that modern climate reserves for warm oceans and rainforest. This presents a serious challenge to the standard picture of ice ages, in which glaciers grow outward from polar caps, but leave central equatorial regions mostly ice-free. Researchers consider various ways to reconcile the new data with older ideas. Perhaps the magnetic field of Earth behaves very differently in the Neoproterozoic, invalidating simple models. Perhaps the rocks have been disturbed, tilted, or remagnetized by later events confusing the signal. Or perhaps the interpretations of the field directions are wrong. Each of these possibilities is tested. Careful fieldwork checks whether the rocks are still in their original orientation. Thermal and chemical experiments probe whether the magnetic minerals have been reset. Independent dating methods help ensure that the glacial layers and the measured magnetic signals truly belong to the same age. Although uncertainties remain, many of the low-latitude results withstand these tests. The simplest reading is that during certain intervals of the Neoproterozoic ice sheets, or large glaciers reach into zones that receive strong sunlight year-round. If that is the case, then average global temperatures must have been far lower than during later ice ages. The idea of a snowball Earth in which ice extends almost to or even across the equator moves from a speculative suggestion to a serious working hypothesis. Other observations support this shift. In several regions, large isolated stones known as drop stones are found within otherwise fine-grained marine sediments of this age. They appear to have been released from floating ice, such as icebergs, into the quiet waters of a deep sea. Their presence far from shore implies that glaciers reached the coast, carved ice into the ocean, and sent rafts of rock-bearing ice out over significant distances. If such features occur at low paleolatitudes, the implication is that seas in tropical zones are at least seasonally covered by ice. Another clue comes from the surfaces of some older rocks that underlie Neoproterozoic tillites. They show not only striations but also wide grooves and chatter marks, consistent with thick, heavy ice moving across them. These scratches sometimes run in directions suggesting that ice flows outward from central regions toward what would then be lower latitudes instead of the other way around. Piece by piece, a picture accumulates of a planet in which ice no longer sits just at the top and bottom, but spreads over large swathes of land and sea in all directions. Yet the record is still incomplete, and interpretations vary. Some geologists propose that the ice reaches into the subtropics, but leaves a band of open or seasonally ice-covered water near the equator, a scenario sometimes called a slush ball Earth. Others note that if sea ice is thick enough and reflective enough in low latitudes, climate feedbacks may push the system into a state where ice does cover almost everything. In either case, tropical glacial deposits represent an anomaly that cannot be ignored. They demand a mechanism for carrying cold far from the poles, for sustaining glaciers under intense sunlight, and for returning the planet to warmer conditions later. They also create a bridge between rocks and models. The same paleomagnetic techniques that show how continents travel over time now show that during certain intervals cold follows them into unexpected zones. The study of ancient glacial sediments thus changes from a regional exercise into a global one. Each new field site, each measured stratum of tillite or layer of dropstone-bearing mud, has the potential to adjust the outline of a worldwide event. In this way, the discovery of ice at the equator becomes not just a curious fact about remote times, but a central constraint on how Earth's climate can behave when pushed away from its usual balance. As evidence accumulates from field sites around the world, the pattern of low-latitude glaciation becomes harder to dismiss as a series of local accidents. At the same time, other more subtle clues begin to surface from the same Neoproterozoic rock sequences. Beyond the obvious tillites and dropstones, geologists find layers of unusual chemical sediments that speak of changes not only in temperature and ice cover, but in the chemistry and circulation of the oceans themselves. These additional lines of evidence gradually turn the idea of Snowball Earth from a loose suggestion into a structured hypothesis. One of the first striking anomalies involves banded iron formations. These are distinctive rocks composed of alternating layers rich in iron, minerals, and silica, often with a rhythmic banded appearance. They are most common in very ancient rocks, more than 2 billion years old, and are usually interpreted as the product of early oceans, in which dissolved iron cycles between reduced and oxidized states, as oxygen levels in the water and atmosphere slowly rise. After about 1.5 billion years ago, banded iron formations become rare, suggesting that the oceans have largely lost their store of dissolved iron and that oxygen has become more abundant. Yet in Neoproterozoic sequences associated with glacial deposits, iron formations make a surprising return. At first glance, this seems out of place. Why would ocean conditions that allow iron to precipitate in this distinctive way reappear so long after they are thought to have vanished? One plausible explanation is that large parts of the ocean become isolated from the atmosphere for an extended time. Under a permanent cover of ice, surface waters would not exchange gases with the air as efficiently as they usually do, and the circulation patterns that mix the ocean from top to bottom could slow or even stall. In such a scenario, deep waters might become depleted in oxygen again and accumulate dissolved iron echoing conditions on the early Earth. When ice eventually retreats and circulation restarts, that iron could be oxidized and deposited in layers, forming a new generation of banded iron formations. This interpretation links the reappearance of these rocks to an ocean sealed beneath ice on a global or near-global scale. Another recurring feature in Neoproterozoic glacial successions is the presence of thick carbonate layers directly above glacial deposits. These so-called cap carbonates drape over tillites in many regions. They often show unusual textures such as giant wave-like structures and delicate crystal fans, and can appear almost the same from Namibia to Australia to China. The fact that such carbonates are found resting immediately on top of glacial sediments suggests a rapid switch from very cold conditions to warmer ones, in which carbonate minerals can precipitate readily from seawater. The chemistry of these cap carbonates, including the ratios of different forms of carbon in them, points toward a major disturbance in the global carbon cycle. One widely discussed explanation is that during a snowball interval, volcanic gases continue to add carbon dioxide to the atmosphere, while weathering of rocks on land slows dramatically under ice. Greenhouse gases therefore build up over millions of years even as the surface stays frozen. When the ice eventually begins to melt, perhaps triggered by this enhanced greenhouse effect, the resulting sudden warming and intense rainfall could strip vast amounts of material from freshly exposed land and deliver it to the oceans. At the same time, high levels of carbon dioxide dissolved in oceans and rain may make the waters more acidic at first, and then gradually oversaturated with respect to carbonate as the system adjusts. The combination of chemical changes, rapid erosion, and warming seas could promote the widespread precipitation of carbonate minerals as a kind of chemical crust or cap over the glacial deposits. The near synchrony of such caps in many parts of the world hints at a common global cause rather than independent regional events. Alongside these rocks, geochemists study the proportions of stable isotopes of carbon and oxygen in Neoproterozoic sediments. These isotopes act as traces of biological productivity, ocean temperature, and global carbon storage. In the run-up to and during some of the inferred snowball events, the carbon isotope record shows large deviations from the values typical of other times. These excursions suggest that the balance between organic carbon buried in sediments and inorganic carbon cycling through the atmosphere and oceans is strongly perturbed. While the details are still debated, many researchers interpret these shifts as further evidence that the planet is passing through an extreme climate state in which usual feedbacks are pushed beyond their normal ranges. As these different observations are pieced together, a conceptual picture of snowball Earth takes shape. In this picture, the Neoproterozoic Earth enters a glaciated state in which ice sheets extend to low latitudes on land, and sea ice covers much of the ocean, perhaps almost entirely. Under this lid, the oceans become stratified, and in places anoxic, allowing dissolved iron to build up. Life is restricted to refuges in thin zones of open water, beneath patches of thinner ice, and around hydrothermal vents. On land, most surfaces are buried under ice and erosion slows. Volcanic gases slowly accumulate in the air because the normal processes that remove carbon dioxide, such as chemical weathering of rocks and uptake by plants, are suppressed. After a long interval in this frozen configuration, greenhouse warming eventually becomes strong enough to thin the ice, exposes dark surfaces, and initiate melting. Once melting starts, the high reflectivity of ice decreases, more sunlight is absorbed, and warming accelerates. The climate moves rapidly into a warm, high carbon dioxide state. Torrential rains and fresh weathering on land deliver a pulse of ions to the oceans, and thick layers of carbonates precipitate in many basins as cap rocks over the glacial deposits. Over further millions of years, the climate relaxes back toward a more temperate configuration. The term snowball Earth is introduced to summarize this sequence, reflecting the idea of a planet that from space would appear almost entirely white. A key period in which several such events occur is named the Cryogenian, meaning frost-forming time. Within this interval, individual glaciations are given names tied to the geological formations in which they are first recognized, such as the Sturtian and the Marinoan. Age estimates based on radiometric dating place these major glaciations roughly between 700 and 600 million years ago. There are hints of additional, possibly shorter, lived glacial episodes in the later Neoproterozoic as well. Each is associated in different regions with its own pattern of glacial sediments, possible banded iron formations, and distinctive overlying carbonates. Despite this increasingly coherent picture, significant uncertainties remain. It is not yet clear whether the ice cover in these events reaches all the way to the equator, or stops short, leaving narrow belts of open or seasonally open water. The duration of individual snowball episodes is still debated, with some estimates suggesting tens of millions of years and others favouring shorter intervals. The exact triggers that push the climate into such an extreme state, and the thresholds that control its exit, are still subjects of active research. Moreover, the fossil record from around these times is sparse and enigmatic, making it difficult to track precisely how life responds to and recovers from such long winters. The snowball Earth hypothesis thus sits at an interesting point between observation and model. It is anchored in concrete measurable features of rocks, such as the orientation of magnetic grains, the presence of tillites and dropstones, the distribution of banded iron formations, and the chemistry of cap carbonates. From these, data scientists infer a global climate state almost entirely unlike the one familiar from human history. Yet the step from regional deposits to a truly global freeze involves assumptions about the behavior of ice oceans and atmosphere that must be tested through climate models and further fieldwork. The hypothesis is therefore both compelling and incomplete. It explains several otherwise puzzling features of the Neoproterozoic rock record and raises new questions about the limits of planetary climate. As pieces of evidence continue to accumulate, the outline of a world almost entirely encased in ice becomes sharper, even as the details of how that world functions and how it transitions back to warmth remain only partially resolved. Beneath a continuous shield of ice, the surface of the Neoproterozoic ocean appears almost motionless from space, but inside the planet's water there is still movement, chemistry, and life. The Snowball Earth hypothesis does not imagine a world in which the oceans are frozen solid to the seafloor. Instead, it points to a thick lid of sea ice, perhaps many hundreds of meters deep, in places under which liquid water persists. At the ice-water boundary, the temperature hovers near the freezing point of seawater, but a short distance below the ocean becomes slightly warmer and more stable. In this dim environment, far from direct contact with the atmosphere, organisms that have already spent more than 1 billion years adapting to varied conditions now face a new arrangement of constraints. There is little or no sunlight reaching the upper layers except where the ice is thinnest or cracked. Gas exchange with the air above is severely reduced. Large-scale circulation patterns that normally bring oxygen-rich surface water down and return nutrient-laden deep water upward are altered or slowed. Yet extinction does not sweep the sea clean. Microbial ecosystems are flexible, and evidence from both ancient rocks and modern extreme environments suggests that several different kinds of refuge are likely to exist. One possible refuge lies around hydrothermal vents on the ocean floor. Here, seawater penetrates down into newly formed crust, heats, up-reacts with rocks, and then rises back into the ocean loaded with dissolved minerals and reduced chemical species. Even under a global ice cover, tectonic activity continues. Mid-ocean ridges still create new crust and vent systems still operate. Chemosynthetic microbes that use chemical gradients rather than sunlight as their energy source can thrive in these settings. They build communities that feed on the warm mineral-rich fluids, and in turn support more complex organisms where such organisms have already evolved. Modern observations of vent ecosystems in the present-day deep sea show dense mats of bacteria, tube worms and various crustaceans living in total darkness, independent of photosynthesis. It is reasonable to imagine that analogous communities exist in the Neoproterozoic oceans, providing a stable anchor for life, even while the surface is locked in ice. A second type of refuge may occur just beneath the ice itself. Even thick sea ice is not a uniform, flawless barrier. It contains channels and pockets of very salty water, known as brine inclusions, formed as ice crystals grow and exclude salt. Thin films of liquid can persist along grain boundaries between crystals. In modern polar seas, such microhabitats are rich in microbial life. Photosynthetic algae and bacteria inhabit brine channels and the underside of ice, where enough light filters through to permit slow but steady growth. Their dark pigments help them absorb scarce photons, and their metabolic machinery is tuned to low temperatures. Over time, they accumulate organic matter that feeds other microorganisms. During a snowball interval, the number and size of such ice-associated ecosystems may be limited, but wherever cracks, ridges, or zones of thinner ice occur, they can exist. Seasonal or longer-term variations in ice thickness, perhaps driven by small changes in solar input or by geothermal heat from below, would open and close these windows. Life that colonizes them might endure cycles of growth and dormancy, freezing and reactivation as conditions fluctuate. A related habitat forms in features called cryoconite holes, which are small water-filled pits that appear on the surface of glaciers and ice sheets when dark grains of dust or rock absorb sunlight and locally enhance melting. On modern Greenland and Antarctic ice, cryoconite holes are widespread, and they often host diverse microbial communities that trap more dust to deepen their basins and maintain liquid water, even when the surrounding surface is frozen hard. In a snowball Earth scenario, meteorite dust, volcanic ash, and fine particles blown by wind could settle on the global ice cover. Where they concentrate, they might generate miniature ponds and slush-filled basins that are colonized by hardy microbes. These microhabitats would be small relative to the size of the planet, but they demonstrate that even on an apparently uniform surface, local conditions can diverge enough to permit liquid water and metabolism. The ocean beneath the ice also has boundaries with continents and volcanic islands that may rise above or close to the sea surface during parts of the snowball episodes. Around such land masses, geothermal heat and pressure from the weight of ice could create networks of subglacial lakes and channels. Modern Antarctica provides a useful analogue. There, even under the present ice sheet, satellite and radar observations reveal hundreds of liquid lakes sandwiched between the ice and the bedrock, some of them tens of kilometers across. Water in these lakes stays liquid due to a combination of pressure heat from the underlying crust and insulating ice above. Microbial life has been detected in samples from some of these environments. In the Neoproterozoic, similar systems could develop on a larger scale. Rivers that continue to flow beneath overlying ice lakes dammed by glacial ridges and pockets of liquid at the base of thick ice sheets would all provide isolated but potentially stable habitats. There is also the deeper question of how photosynthetic life, which depends on light, survives prolonged snowball conditions. Fossils and molecular studies suggest that algae and simple multicellular organisms are already present before and after the cryogenian glaciations. Their continuity implies that photosynthesis is not entirely shut down. Thin ice in equatorial or coastal regions, polynyas, where wind or currents keep small patches of ocean free of ice, and transient open water created by volcanism or shifting ice could all allow light to reach the sea surface. In these limited areas, algae could bloom during favourable periods and then form resting stages or spores to endure darker times. The scarcity of such opportunities would place strong selective pressure on these organisms, favouring those that can tolerate cold, low light and long intervals of metabolic slowdown. In this way, the extreme climate acts as a filter rather than a simple destroyer. Life that passes through the filter may carry new adaptations forward into the warmer world that follows. While direct fossil evidence from the snowball intervals is sparse rocks from just after the final great Neoproterozoic glaciations contain impressions and casts of large, soft-bodied organisms collectively known as Ediacaran biota. Their exact relationships to later animals remain uncertain, but their appearance soon after the global freeze suggests that complexity is not permanently set back. Instead, a phase of relative ecological simplicity during the snowball may prepare the stage for later diversification by clearing ecological space and altering global cycles of nutrients and oxygen. The hypothesis that snowball Earth episodes act as both crises and opportunities for life is difficult to test directly, yet it remains consistent with the available evidence. Microbial resilience in extreme environments, the existence of multiple kinds of physical refugees, and the timing of later evolutionary innovations together support the idea that even under thick ice, the biosphere never fully shuts down. Instead, it reorganizes around new niches, maintains a reduced but persistent level of activity, and quietly accumulates the genetic and ecological changes that will matter greatly once sunlight and open water return in abundance. In this view, The frozen surface is not only a sign of planetary hardship, but also a temporary cover under which new possibilities are assembled. The idea that ice once reached into the tropics raises a clear next question. What sort of chain of events can drive a planet from a state with seasonal polar caps, open oceans and active weather into one where glaciers and sea ice extend almost everywhere? To answer this, scientists treat Earth not just as a collection of landscapes and rocks, but as a single physical system in which sunlight, air, water and rock interact through feedbacks. A feedback is a process in which a change in one part of the system causes further changes that either amplify or dampen the original shift. In the case of Snowball Earth, researchers focus in particular on positive feedbacks that tend to reinforce cooling once it begins. One of the most important of these feedbacks involves the reflectivity of the planet's surface known as albedo. Snow and ice are bright, reflecting a large fraction of incoming sunlight back into space, while liquid water and dark rock absorb much more. If conditions cool slightly, polar ice caps grow and snow lines move to lower latitudes. This increase in bright area means more sunlight is reflected, so less energy is absorbed by the surface, which in turn promotes further cooling and further ice growth. In principle, this process can accelerate until ice reaches latitudes where sunlight is normally strong, at which point the effect becomes even more powerful. Simple climate models constructed in the mid-20th century, some of them developed by researchers in the Soviet Union and elsewhere, describe this behavior by dividing the planet into latitude bands and calculating how temperature, albedo, and incoming radiation interact. These models suggest that if ice advances beyond a critical latitude somewhere in the subtropics, the cooling feedback from increasing reflectivity can overpower the warming influence of the remaining dark ocean. Once that threshold is crossed, the ice line may race toward the equator, and the planet could slip into a stable state in which almost all sunlight is bounced back into space. The details of these early models are simplified, but the basic message is clear. Earth's climate has multiple possible stable states. One of them is the familiar configuration with limited ice, and another is a deeply frozen state. The planet can move between them if pushed hard enough. This still leaves open what provides the initial push. Several mechanisms are considered. One broad class of explanations involves long-term changes in the concentration of greenhouse gases, especially carbon dioxide in the atmosphere. Greenhouse gases allow sunlight to reach the surface but trap some of the outgoing infrared radiation warming the planet. If the amount of carbon dioxide in the air decreases significantly, the greenhouse effect weakens and the surface cools. Over geological time, the main way carbon dioxide is removed from the atmosphere is through chemical weathering of silicate rocks on land. Rainwater reacts with minerals aided by dissolved carbon dioxide and forms dissolved ions that are carried to the sea where they can eventually end up in carbonate minerals or a new crust. The rate of this weathering depends on temperature, rainfall, and the distribution of land. During the Neoproterozoic, continents assemble and break apart into configurations that include large land masses straddling the equator. When land lies in the deep tropics, it experiences intense sunlight and high temperatures, which can drive vigorous weathering and rainfall. Some climate and geochemical models suggest that this arrangement could pull down carbon dioxide more rapidly than volcanic outgassing replenishes it, slowly lowering the greenhouse effect over millions of years. As carbon dioxide falls, global temperatures decline. Ice begins to accumulate at high latitudes. The albedo feedback then takes over, allowing the cooling trend to accelerate. In this view, the initial driver of Snowball Earth is a particular continental layout that enhances the efficiency of the long-term carbon cycle. Another class of mechanisms involves shorter-term reductions in incoming solar radiation. Variations in Earth's orbit and axial tilt over tens to hundreds of thousands of years, known as Milankovitch cycles, are well documented for later ice ages and affect the distribution of sunlight between seasons and latitudes. If these cycles line up in certain ways when greenhouse gas levels are already low, they can produce especially cold summers in polar regions, allowing snow and ice to accumulate over successive years. Over longer spans, the overall output of the Sun itself has changed slowly, but during the Neoproterozoic, it is not thought to vary enough to explain a sudden deep freeze on its own. However, transient events such as massive volcanic eruptions or large asteroid impacts can inject dust and sulfate aerosols into the stratosphere, temporarily shading the planet by reflecting sunlight. Modern observations of eruptions show measurable cooling for a few years following major events. If in the Neoproterozoic, a period of already declining greenhouse gases coincides with a cluster of large eruptions, the combined effect could push the climate past the critical threshold where ice growth becomes self-reinforcing. There is also the possibility that biological evolution contributes to these shifts. The spread of new, more productive forms of photosynthetic life, such as certain types of plankton or algae, can increase the rate at which carbon dioxide is drawn down from the atmosphere and buried as organic carbon. Before the cryogenian microbial mats and simple eukaryotic organisms already inhabit shallow seas. If some evolutionary innovation allows them to colonize new environments or photosynthesize more efficiently, they may briefly outpace the balance of the carbon cycle, drawing down greenhouse gases and contributing to cooling. This link between life and climate is already recognized in earlier events such as the Great Oxidation Event more than 2 billion years ago, when the rise of oxygen-producing microbes leads to major atmospheric changes and a very long glaciation. Whether a similar biological trigger operates for Neoproterozoic snowball Earths is still uncertain, but it remains a plausible part of the picture. Despite these ideas, there is no single smoking gun that definitively identifies the initial cause of any one Neoproterozoic glaciation. Instead, the current view is that several factors may align. A continental configuration that favours strong weathering and carbon dioxide removal, slow background evolution in the brightness of the Sun, orbital variations that alter seasonal contrasts, and occasional bursts of volcanic or impact-derived aerosols could together push the climate toward a tipping point. Once ice extends to low enough latitudes, the albedo feedback can then take over, driving the system the rest of the way into a snowball state. Climate models built with much more detail than the early energy balance schemes using numerical methods and computing power developed in the late 20th and early 21st centuries explore these scenarios. They divide the atmosphere and ocean into three-dimensional grids and simulate winds, currents, clouds, and sea ice. When these models are given lower greenhouse gas concentrations, appropriate continental positions, and a slightly dimmer sun consistent with the Neoproterozoic, some runs do indeed produce equatorial ice and near global sea ice cover. Others produce slushball states with persistent open water near the equator. The outcome depends sensitively on uncertain parameters such as how reflective different types of clouds are, how easily snow accumulates on sea ice, and how ocean currents respond to changes in salinity and temperature. This sensitivity itself is telling. It indicates that Earth's climate near the boundary between partial and global glaciation is a delicate system where small changes can have large effects. From a scientific perspective, this delicacy is both a challenge and an opportunity. It means that reconstructing the exact path into a snowball Earth requires careful integration of many lines of evidence, from the chemistry of ancient rain-altered rocks to the geometry of fossil shorelines. It also underscores the idea that the climate has built-in thresholds. Once crossed, these thresholds can lead to conditions that feel disproportionate to the initial disturbance. The machinery of planetary freeze is thus not a simple on-off switch, but a network of interacting processes. Some pieces, such as the ice albedo feedback and the long-term carbon cycle, are well established in principle and can be demonstrated in modern observations and experiments. Others, such as the precise role of tropical continents or the influence of evolving biospheres are constrained but still open to refinement. The Snowball Earth episodes of the Neoproterozoic, inferred from scattered rocks and subtle isotopic signals, become test cases for how far this machinery can be pushed. They suggest that Earth's climate, usually buffered by stabilizing feedbacks, can under certain arrangements be drawn into an extreme state that persists until a different set of feedbacks takes over. Understanding how the freeze begins is only half of the story. The same network of processes must also contain a route out of the frozen state, or the planet would remain locked in ice indefinitely. In the Neoproterozoic, that route appears to involve the gradual accumulation of greenhouse gases while weathering is suppressed. The details of this recovery and the violent warmth that may follow involve their own feedbacks and uncertainties, and they link the coldest times in Earth's history to later bursts of heat and chemical change recorded in cap carbonates. In this way, the machinery that drives the planet into a snowball state is closely tied to the machinery that eventually melts it again, forming a complete, if still partly obscured cycle between extremes. Under a snowball Earth configuration, the planet's surface appears stable on human timescales, but deep time continues to pass. Ice sheets flow slowly thickening, where snowfall, however sparse, still adds mass and thinning, where sublimation and calving remove it. The oceans beneath their lid continue to circulate even if weakly, and tectonic plates keep drifting, colliding, and being consumed at subduction zones. Volcanoes erupt along mid-ocean ridges and at continental margins. With each eruption, gases are injected into the atmosphere above the frozen surface. Among these gases, carbon dioxide and methane are particularly important for climate. Ordinarily, the long-term carbon cycle balances volcanic emissions with processes that remove carbon dioxide from the air. Rainfall dissolves the gas, forming weak carbonic acid that reacts with silicate rocks, breaking them down in a sequence of reactions called chemical weathering. Rivers carry the resulting ions to the sea, where they can eventually form carbonate minerals that lock carbon away for millions of years. Living organisms also contribute using carbon dioxide for photosynthesis and secreting shells that later become limestone. In a world covered by ice, many of these pathways are weakened. Thick ice shields most land from direct contact with the atmosphere and liquid water. Rainfall is greatly reduced because evaporation from ice-covered oceans is limited. Vegetation on land is largely absent. As a result, chemical weathering slows to a fraction of its former rate. Volcanic outgassing, however, continues at roughly the same pace as before because it is driven by the planet's internal heat and plate motions rather than surface climate. The imbalance is gradual but inexorable. Year after year, century after century, carbon dioxide accumulates in the atmosphere, and methane from volcanic and possible biological sources adds to the greenhouse effect. Despite the high albedo of the ice, the infrared trapping capacity of these gases increases. Climate models that incorporate this greenhouse buildup suggest that over several million years, atmospheric carbon dioxide could reach concentrations far higher than any recorded in the later Phanerozoic era, when complex animals and plants dominate. During most of the snowball interval, the reflective ice compensates for this added greenhouse trapping, keeping surface temperatures below freezing. However, the balance between reflection and insulation is not fixed. At some point, the concentration of greenhouse gases becomes large enough that even a small reduction in ice cover could trigger net warming. The question then shifts from whether the climate can leave the snowball state to how and where the first cracks in the icy shell appear. One plausible route involves regions where the ice is already thin, such as around volcanic hotspots, or where ocean currents concentrate slightly warmer water against the underside of the ice. Localized melting could expose patches of darker surface, whether open water or bare rock. These darker patches absorb more sunlight than surrounding ice. The absorbed energy further warms the local environment, expanding the melt area. In this way, a small perturbation can grow. Once exposed, liquid water and rock surfaces also allow more rapid exchange of heat and moisture between ocean, land, and atmosphere, making it easier for additional ice to melt nearby. As the greenhouse effect strengthens, seasonal cycles regain influence. Summers at some latitudes may start to be just warm enough to produce surface melt on sea ice and ice sheets, even if winters remain extremely cold. Meltwater ponds form and drain. Snow develops layers of crust and slush. The effective albedo of these mixed surfaces decreases compared with clean, bright ice, allowing additional absorption of solar energy. This seasonal amplification can accelerate the transition, as each summer removes slightly more ice than the previous one. The climate system begins to move away from the snowball attractor toward a warmer state. Once a critical fraction of the surface has darkened, the feedback reverses. Instead of cooling, building on itself, warming starts to reinforce further warming. Ice retreats poleward, sometimes rapidly on geological timescales. Numerical simulations indicate that the shift from a fully glaciated planet to one with largely ice-free low latitudes could occur over a few thousand to tens of thousands of years, which is abrupt compared with the millions of years spent in the frozen phase. The weather experienced during this deglaciation would be extreme by modern standards. With very high concentrations of greenhouse gases and fresh dark surfaces exposed, the lower atmosphere could heat up significantly. Air laden with moisture evaporated from newly opened seas would rise, condense, and fall as intense precipitation. Torrential rains would hammer bare rock which has been freshly exhumed from under ice, with little soil or vegetation to protect it. Floods and debris flows would sweep across lowlands. On slopes, rapid melting and mechanical failure of ice could generate landslides and outburst floods, draining subglacial lakes in sudden pulses. Chemical reactions between carbon dioxide-rich rainwater and exposed minerals would be vigorous. This accelerated weathering would deliver large amounts of dissolved calcium, magnesium, and bicarbonate ions to the oceans. At the same time, the oceans themselves would be adjusting to rapid changes. As ice melts, fresh water pours into the surface, layers reducing salinity and density. This influx can alter circulation patterns, potentially disrupting existing stratification. Oxygen from the atmosphere can once again dissolve into the sea, starting to reventilate deep waters that may have been anoxic for long periods. The influx of ions from weathering combined with high levels of dissolved inorganic carbon could push surface waters toward conditions favorable for the precipitation of carbonate minerals. Under such circumstances, calcium carbonate might form rapidly, coating seafloors and any available substrates with new layers. These processes offer a natural explanation for cap carbonates, observed directly above Neoproterozoic glacial deposits. Their global distribution and consistent position at the top of glacial sequences suggest that they are products of this intense short-lived chemical rebalancing. The textures seen in some cap carbonates, such as large wave-like structures and radial crystal fans, may reflect precipitation in saturated turbulent waters under conditions unlike those of typical Phanerozoic seas. Within the ocean, ecosystems would be undergoing sharp transitions. Organisms that survive the snowball interval in refuges must now adapt to rising temperatures, changing salinity and expanding habitable zones. Photosynthetic life in particular would experience a sudden and dramatic increase in available light and space. Coastal upwelling in a reventilated ocean would bring nutrients to the surface, possibly fueling blooms of algae and cyanobacteria. These blooms would draw down some of the excess carbon dioxide, contributing to a gradual dampening of the extreme greenhouse state. As organic matter sinks and is buried, it locks away carbon that had previously been in the atmosphere. In the longer term, this burial may help stabilize climate in a new equilibrium with less ice and more temperate conditions. On land, the retreat of ice sheets leaves behind landscapes shaped by glacial erosion. over-deepened basins become lakes, moraines and drumlins mark former ice limits. In the Neo-Proterozoic, there is as yet no complex terrestrial plant life to colonize these areas, but microbial mats and simple eukaryotes can spread across wet surfaces, beginning the slow process of forming soils. Weathering of freshly exposed bedrock combined with biological activity will continue to influence atmospheric composition over millions of years. The deglaciation phase thus represents not only the physical melting of ice, but a wholesale reorganization of surface environments and geochemical cycles. Despite the violence of the transition, there is no indication that life is erased. Instead, the biosphere is carried from one extreme climate state into another, and in doing so it may pass through a sequence of bottlenecks and expansions that affect later evolution. The timing of the final Neoproterozoic glaciations relative to the rise of large soft-bodied organisms, and later the Cambrian explosion of animal diversity, has led some researchers to propose that the snowball episodes contribute indirectly to these biological events. The mechanism is not yet clear, but several possibilities exist. Reoxygenation of the oceans during deglaciation could provide a more favourable environment for larger, more metabolically demanding organisms. The physical restructuring of habitats might open new ecological niches. Pulses of nutrient supply from intense weathering and upwelling could drive bursts of productivity and evolutionary innovation. While these ideas extend beyond what can be firmly established from the rock record alone, they follow naturally from the climate and geochemical changes implied by snowball Earth models. The process of melting a frozen planet, therefore, is more than just a reversal of cooling. It is an episode that couples the deep carbon cycle surface weathering ocean chemistry and biological evolution in a tightly intertwined sequence. The details of timing, magnitude, and feedback strength remain subjects of active investigation, but the general outline supports the view that once Earth enters a snowball state, the same geophysical forces that froze it eventually warm it again, overshooting into a hot, wet aftermath before settling into a more moderate climate. This oscillation between global cold and post-glacial heat marks some of the most dramatic swings recorded in Earth's history, and leaves a lasting imprint not only in rocks and minerals but in the trajectory of life itself. As the snowball Earth hypothesis gains attention, it also attracts detailed scrutiny. The idea of a planet almost entirely sealed in ice is a strong claim, and in science, strong claims require equally strong evidence. Each piece of data assembled in favour of global glaciation must withstand attempts to explain it in less extreme ways. In laboratories and at conference tables, researchers examine the same rock samples and field reports, but sometimes arrive at contrasting conclusions. These debates do not simply weaken the snowball hypothesis, they refine it and highlight areas where the geological record is ambiguous. Some lines of criticism focus on the interpretation of supposed glacial deposits. Tillites, dropstones, and striated pavements are not unique to glaciers. Similar-looking rocks can be produced by large underwater landslides known as mass transport deposits, or by debris flows on continental slopes. In such settings, a slurry of mud and rock moves downslope under gravity entraining blocks of various sizes, and depositing them chaotically when it slows. The resulting mixture of clasts and matrix can resemble glacial till. Large clasts embedded in fine-grained sediments are often taken as iceberg dropstones, but they can also be supplied by slope failures or volcanic activity. In some Neoproterozoic sequences, careful mapping suggests that at least part of the thickness, originally labelled as glacial, may instead represent such non-glacial mass flows. In these cases, the extent and duration of ice inferred from the rocks might need to be reduced. Another source of uncertainty comes from the paleomagnetic data used to assign low latitudes to glacial units. The method assumes that Earth's magnetic field behaves roughly as a dipole, aligned with the rotation axis over long times, and that the recorded directions in rocks have not been significantly altered since formation. Yet the field can wander tilt and reverse its polarity on timescales of thousands to millions of years. In addition, some rocks can acquire secondary magnetization during heating deformation or chemical changes long after they first form. Critics of snowball Earth scenarios point out that if during part of the Neoproterozoic the magnetic field is organized differently, or if the samples measured are affected by later processes, then reconstructions of original latitude could be misleading. A rock thought to have formed at the equator might in fact have originated at mid-latitudes. To address this, specialists in rock magnetism carry out tests designed to separate primary and secondary components in the magnetic signal. They progressively heat or chemically treat samples to see at what point certain directions are lost. If a stable component persists to high temperatures and has a direction consistent across many sites, confidence grows that it records the original field. Even so, some datasets remain ambiguous. There is also the phenomenon of true polar wander, in which the entire solid shell of the planet can reorient relative to the rotation axis, causing all continents to move together in latitude. Evidence for such events comes from other parts of the geological record, and if they occur during the Neoproterozoic, they could complicate simple interpretations based on paleomagnetism. A different set of observations raises questions about the completeness of global ice cover. Certain sedimentary structures such as wave-formed ripples and cross-bedding, typical of shallow agitated water, are present in some rocks of cryogenian age. The presence of these features in layers close to glacial deposits suggests that at least locally open water exists under wind-driven waves. Some limestone units that form during or between glacial intervals host signs of normal marine life, implying that conditions in parts of the ocean remain relatively mild. These observations support variants of the original hypothesis, in which the Earth is very icy but not entirely locked in. In the slushball Earth scenario, thick ice blankets much of the planet, but a belt of seasonally open or thinly ice-covered ocean persists around the equator. This permits continued exchange of gases between atmosphere and ocean, some ongoing photosynthesis in surface waters, and a reduced need for extreme carbon dioxide buildup to terminate the glaciation. Models constructed with different assumptions about cloud behavior and ocean heat transport sometimes favor such slushball states over fully frozen ones. The rock record alone is often insufficient to distinguish sharply between these possibilities. At the same time, there are features that seem easier to explain with extensive, long-lasting ice cover. The recurrence of cap carbonates directly above glacial units on multiple continents. Their unusual textures and their strongly shifted carbon isotope signatures suggest a globally coherent post-glacial event. Simple regionally restricted glaciations would be less likely to produce such nearly simultaneous chemical signals worldwide. Banded iron formations that reappear only during the most intense glacial intervals also hint at large parts of the ocean being cut off from contact with the atmosphere for extended periods. These constraints make it difficult to shrink the snowball Earth concept down to a series of ordinary ice ages without losing explanatory power. There is also the matter of timing. Radiometric dating of volcanic ash layers, bracketing glacial deposits combined with indirect chronometers, such as the decay of certain radioactive isotopes in carbonate sequences, suggests that some Neoproterozoic glaciations last several million years. This is far longer than typical Pleistocene ice ages, which unfold over tens to hundreds of thousands of years. Maintaining large ice sheets near the equator for such long spans requires a persistent global mechanism, not just local mountain glaciation. Even those who favour slushball models usually accept that the cryogenian events are exceptional in both scale and duration. The ongoing debates over the extent of ice lead to a more nuanced picture, in which snowball and slushball states may represent different points along a continuum of extreme climates. In some episodes, sea ice may be continuous from pole to pole, interrupted only by rare patches of thin ice. In others, narrow equatorial seaways may remain partially open, acting as critical conduits for heat and moisture. The geological and geochemical records, limited by erosion metamorphism and gaps in sedimentation, cannot provide a complete map of these conditions. Instead, they offer snapshots from which scientists attempt to reconstruct a continuous film. Modern observational tools add further context. Studies of Mars and icy moons in the outer solar system, such as Europa and Enceladus, show that worlds with thick ice shells and subsurface oceans are not rare. Although their sizes, compositions, and energy sources differ from Earth's, they demonstrate the physical plausibility of long-lived ice-covered oceans. Satellite measurements of current polar regions on Earth reveal how sea ice forms, moves, and melts, providing analogues for processes that may have operated on a grander scale in the past. These comparisons do not settle the question of exactly how global Neoproterozoic glaciations are, but they extend the conceptual framework in which the question is posed. Underneath the technical disagreements lies a shared recognition that the Cryogenian stands out as a time when climate pushes against its own boundaries. Whether the planet is entirely white or mottled with bands of slush, the combination of low-latitude ice, unusual ocean chemistry, and strong carbon cycle disturbances marks a distinct mode of operation for the Earth system. The unresolved aspects of the snowball debate, including the precise distribution of ice and water and the details of magnetic field behavior, therefore serve not as a weakness in the broader story, but as reminders of the scale of the puzzle. With each new drill core, each reanalyzed magnetic sample, and each improved climate model, the view of these ancient winters becomes a little clearer, while still leaving room for uncertainty about exactly how close to complete freezing the planet once came. When the last major Neoproterozoic ice sheets retreat and the climate settles into a more temperate state, Earth does not simply return to a previous baseline. Conditions after the Cryogenian differ in important ways from those before it. The atmosphere holds more oxygen, the oceans circulate differently, and the surface environments available for life are reorganized. The rock record from the interval that follows, known as the Ediacaran period, preserves signs that these changes matter for biology. Large, soft-bodied organisms appear in sediments laid down on continental shelves and in shallow seas. Their impressions preserved as moulds and casts in sandstone and siltstone show fronds, discs, quilted forms, and branching bodies that are much larger than any fossils known from earlier times. Some reach tens of centimeters in length. Their classification remains uncertain, but they demonstrate that multicellular life with complex body plans is now present. Geochemical measurements from Ediacaran rocks point toward a stepwise increase in the amount of free oxygen dissolved in seawater and stored in the atmosphere. Before and during the Cryogenian glaciations, oxygen levels are thought to be low and patchy, with significant parts of the deep ocean remaining anoxic. As deglaciation proceeds and surface waters warm, the re-establishment of vigorous circulation helps ventilate the interior of the oceans. At the same time, intense weathering of freshly exposed rock delivers nutrients such as phosphorus to coastal zones, stimulating photosynthesis. Cyanobacteria and algae pump oxygen into the environment more efficiently. Burial of organic matter in postglacial sediments locks away reduced carbon and allows oxygen to accumulate further. Over millions of years, this combination of processes likely lifts oxygen levels above critical thresholds required to sustain larger, more metabolically demanding organisms. The timing is not perfectly resolved, but radiometric ages indicate that the final Cryogenian glaciation ends only a few million years before the first widespread appearance of Ediacaran macrofossils. This proximity invites the idea that the climate crisis and its aftermath help prepare the conditions for new forms of life to flourish. The details of this linkage remain a topic of research. One possibility is that the snowball events strip away many earlier ecosystems, reducing competition and opening ecological space. Surviving lineages already adapted to stress can then diversify into new niches as environments become more varied again. Another is that the chemical changes driven by prolonged ice cover and abrupt deglaciation alter the availability of trace metals required for enzymes and cellular machinery, nudging evolution towards certain biochemical pathways. Whatever the precise connections, the Neoproterozoic does not end with a simple return to the status quo. It transitions into a world where the interplay between oxygen, nutrients, and biological complexity is shifting. The Ediacaran organisms themselves are peculiar. Many lack obvious hard parts, and their mode of life is difficult to infer. Some seem anchored to the seafloor, absorbing nutrients from the water, or through symbiosis with photosynthetic microbes. Others may glide slowly over microbial mats, leaving subtle trace fossils. Their shapes do not map neatly onto later animal groups. Some researchers propose that they represent early experiments in multicellularity that leave no direct descendants, while others suggest that at least some are related to stem groups of modern animals such as cnidarians or bilaterians. In either case, their emergence after the snowball interval underscores that large-scale organismal innovation is taking place. The physical environment they inhabit is also evolving. Continental margins continue to rift and reorganize as the supercontinent that dominates the Neoproterozoic breaks apart. New ocean basins open changing patterns of currents and upwelling. Sedimentary records indicate alternating intervals of oxygen, rich and oxygen-poor conditions in different basins during the Ediacaran, suggesting that the system is still finding a new equilibrium. Local redox fluctuations could generate a patchwork of habitable and stressful zones, further shaping evolutionary pathways. In the early Cambrian period that follows the Ediacaran, the fossil record shows an abrupt increase in the diversity and disparity of animal forms. This interval, often called the Cambrian explosion, sees the appearance of many major animal groups with hard skeletons, complex sensory systems, and active behaviours. Trace fossils record the spread of burrowing, crawling, and swimming through marine sediments. Body fossils in certain Lagerstätten reveal intricate anatomies. Although the Cambrian explosion takes place tens of millions of years after the last snowball Earth events, some scientists view it as part of a broader narrative in which the Neoproterozoic glaciations act as one of several preconditions. The rise in oxygen, the restructuring of nutrient cycles, and the reorganization of habitats following global or near-global glaciation may set the stage on which Cambrian animals later radiate. From this perspective, snowball Earth episodes are not isolated curiosities but key transitions in the co-evolution of climate and life. They mark times when the physical environment shifts so strongly that biology responds not simply by adjusting ranges, but by exploring new organizational levels. There is also a long-term climatic aspect to the aftermath. The regulation of carbon dioxide through weathering resumes under new boundary conditions. In the post-glacial world, continents are distributed differently, and mountain belts formed during the assembly of earlier supercontinents are subject to erosion. The balance between carbon dioxide input from volcanoes and removal by weathering and burial settles into a regime that sustains a mostly ice-free planet for extended periods, interrupted by smaller-scale glaciations, but not by further snowball events. This suggests that the Neoproterozoic snowball episodes may represent a time when the climate system samples an extreme state, and then through feedbacks and long-term processes moves away from it into a mode that is less prone to full global freezing. The reasons for this shift are still being investigated. They may include the gradual brightening of the sun, which makes deep global glaciation harder to achieve for the same greenhouse gas concentrations, and the progressive influence of land plants later in the Phanerozoic, which change the nature of weathering and carbon storage. Seen against this background, the Neoproterozoic stands as a hinge between a more unstable early Earth and a somewhat more buffered later Earth. For planetary science, this has broader implications. It shows that even a world in the habitable zone of its star can, for significant intervals, experience conditions that seem in retrospect close to the limits of habitability. Yet life persists, and after crisis sometimes flourishes in new ways. The exact chain of cause and effect between snowball Earth events, the rise of complex multicellular life, and the Cambrian radiation remains partly speculative, but it is grounded in a sequence of observed changes. Glacial deposits at low latitudes testify to exceptional cold. Cap carbonates and iron formations point to profound alterations in ocean chemistry. Isotope records trace shifts in the global carbon and oxygen cycles. Fossils in overlying strata reveal a stepwise increase in organism size and complexity. Together, these lines of evidence support a picture in which the coldest intervals in Earth's history are not simply interruptions in an otherwise smooth progression, but active parts of that progression. They reset environmental parameters, redistribute resources, and perhaps test the resilience of evolving life. The planet that emerges is not identical to the one that entered the freeze. It carries in its rocks and in its living systems the marks of passage through a regime of climate and habitability that remains even now only partly understood. In the modern world, ice still shapes coasts and climates, but its domain is smaller than during the last glacial maximum, and far smaller than in any snowball interval. Permanent ice now occupies high mountains, Greenland, Antarctica, and parts of the Arctic Ocean. Around these remaining centres of cold, the atmosphere and oceans circulate moving heat and moisture from low latitudes to high and back again. Human societies develop and thrive during a relatively stable climatic period known as the Holocene, in which temperature variations are modest compared with the swings of earlier geological ages. Within this gentle background, however, a new forcing begins to act. The combustion of coal oil and gas, the clearing of forests, and the production of cement release carbon dioxide and other greenhouse gases into the atmosphere at a rate that on geological timescales is abrupt. Instrument records and ice core data show a steep rise in atmospheric carbon dioxide concentration from pre-industrial values to levels not seen for several million years. Alongside this change, global average temperatures increase, glaciers retreat, sea ice shrinks, and patterns of rainfall shift. This modern warming is in magnitude and direction the opposite of the cooling that leads into snowball Earth states, yet it engages some of the same feedbacks and processes. One of these is again albedo. As Arctic sea ice thins and retreats in summer, larger areas of dark ocean are exposed. They absorb more solar radiation than the bright ice they replace warming surface waters and the air above. This warming in turn makes it easier for ice to melt in subsequent seasons, reinforcing the trend. On land, the retreat of mountain glaciers and the shrinking of seasonal snow cover expose darker rock and soil, further lowering reflectivity. Observations from satellites confirm that the planet's average albedo has decreased slightly over recent decades, consistent with these changes. Another feedback involves frozen ground in high northern latitudes. Large regions of Siberia, Alaska, and northern Canada are underlain by permafrost soil and sediment that remain frozen for long intervals. This frozen ground traps organic material that, if thawed, can decompose and release carbon dioxide and methane. As the climate warms, the upper layers of permafrost begin to thaw more deeply each summer, and in some areas permanently. This allows microbial activity to increase, turning previously inert carbon stores into active parts of the atmospheric greenhouse budget. Methane is particularly effective at trapping heat over short timescales, so its release amplifies warming. This is a positive feedback analogous in structure to the snowball albedo feedback, though operating under opposite temperature trends. In the oceans, warming alters circulation and stratification. Surface waters become warmer, and in some regions fresher due to increased rainfall and ice melt. This can make them less dense, inhibiting the sinking motions that drive deep, overturning circulation. Changes in this circulation affect how heat and carbon are stored in the ocean interior and how nutrients are supplied to surface ecosystems. Instrument arrays and satellite altimetry detect shifts in currents, water mass properties and sea level patterns that align with expectations from climate models forced by greenhouse gas increases. The long-term carbon cycle that plays a central role in snowball Earth scenarios is also engaged but on a different timescale. Human emissions add carbon dioxide to the atmosphere much faster than most natural geological processes. Chemical weathering and carbonate formation still act to remove carbon in the long run, but they cannot keep up over centuries or millennia. The result is an accumulation of greenhouse gases that, unlike the gradual build-up under an ice-covered Earth, begins from a relatively warm baseline and pushes the climate further into a warm state. In this context, the Snowball Earth episodes become reference points for understanding the strength and limits of feedbacks. They show that the climate system is capable of large transitions when external or internal forcings cross certain thresholds. Although the direction of change is currently toward warming rather than cooling, the existence of past tipping points suggests that thresholds may also exist on the warm side. Some modelling studies explore possibilities such as the irreversible loss of major ice sheets, the collapse of parts of ocean circulation, or abrupt changes in regional rainfall patterns if greenhouse gas concentrations continue to rise. These potential shifts are not directly analogous to the global freezes of the Neoproterozoic, but they share the characteristic that small changes in forcing, once a critical level is passed, can lead to disproportionate changes in state. Satellite instruments, ocean buoys and ground-based observatories now provide a dense, continuous record of Earth's climate. Agencies such as NASA, ESA, National Meteorological Offices, and international scientific panels assemble these data into assessments that track the trajectory of warming and its impacts. Ice cores drilled in Greenland and Antarctica extend this observational window back through hundreds of thousands of years, revealing cycles of glaciation and deglaciation, driven by orbital variations and modulated by greenhouse gases. Against this backdrop, the current rapid warming stands out as unusual in both speed and cause. The cryogenian snowball events are far more extreme in absolute terms, but they unfold and recover over millions of years. The present experiment with atmospheric composition proceeds over centuries. The rock record also records episodes of natural greenhouse warming, such as the Paleocene-Eocene thermal maximum, during which a large release of carbon leads to a notable global temperature increase. These events, like Snowball Earth, provide analogues and cautionary examples. They show that carbon cycle disturbances, whether toward cold or heat, can leave long-lasting marks on ocean chemistry, sedimentation patterns, and biological communities. From a planetary perspective, the key insight is that habitable conditions are not fixed. Even within the broad zone around a star where liquid water is possible, internal feedbacks can move a planet toward ice-covered or greenhouse-dominated states. Earth has sampled both colder and warmer regimes in its history and has returned from them, but the pathways are not symmetric. Freezing a planet from a temperate state requires a sustained combination of low greenhouse gas levels, suitable continental configurations, and perhaps favourable orbital conditions. Warming a planet from a snowball state requires the slow accumulation of greenhouse gases while weathering is suppressed. Today, the input of carbon is being supplied by human activity rather than by volcanoes beneath ice, and the climate begins from a relatively mild baseline. The endpoint of this perturbation depends on how long emissions continue and how strong the reinforcing feedbacks prove to be. The memory of snowball Earth is stored not only in ancient rocks, but also in the frameworks used to understand climate. Models that reproduce equatorial ice in the Neoproterozoic must correctly handle radiative transfer fluid dynamics and feedbacks. The same physical principles apply when these models are used to project future warming. Ice core analyses that link past temperature changes to greenhouse gas concentrations provide empirical constraints on climate sensitivity. Studies of cap carbonates and their associated isotopic excursions offer examples of how the carbon cycle behaves when strongly disturbed. Even the recognition that life can persist under extreme cold in fragments of habitat beneath ice informs the search for life on other worlds and the assessment of resilience on this one. In a sense, the story of the winter that lasts for 100,000 years and the winters that may have lasted for tens of millions of years converge with the story of a rapid modern warming. They illustrate that Earth's climate, while often stable enough to support the slow unfolding of evolution and human history, is capable of entering unusual states when boundary conditions change. The present is not a replay of the Cryogenian, but it is another chapter in the same long narrative of a planet whose temperature, ice cover, and atmosphere are entwined. In this narrative, the caves of Lascaux, the Antarctic journeys of early explorers, the ancient glacial pavements in Australia and Namibia, and the readings from modern satellites are all points along a continuous curve. They show a world that moves between frozen and temperate modes, between low and high oxygen, between simple and complex life, under the influence of internal cycles and external forcings. The full range of possible future paths is not yet known, but the deep past provides boundaries and examples. A planet that once nearly froze solid and later supported forest dinosaurs, ice ages, and human civilizations is now being nudged in a new direction. The outcome will depend on the interplay of physical laws that have operated since the Neoproterozoic and the recent brief actions of a single species that has learned to read the stories written in stone and ice.